Jeremy Grantham lecture on climate change. Just to give you a brief background, since this center was established in 2009, one of the requirements is every year we hold at least one lecture on climate change by an eminent scientist from anywhere in the world who can look at issues related to the science of climate change, impact of climate change, mitigate climate change, and other issues. Okay, and we have been lucky so far. We have had 18 lectures delivered in the last 15 years, covering a wide spectrum of topics involving paleoclimate, involving climate change impact. Last year it was on energy-related issues related to climate change. So this year we are lucky to get a very eminent, well-known scientist who has worked on monsoon all his career to give the 19th lecture, Jeremy Grantham lecture. So let me say a few words about Dr. Madhavan Rajivan, who is right now Vice Chancellor of the Attrio University. He has worked in many departments of the government. He started at Tata Institute of Fundamental Research and then in the astronomy group, then moved on to the India Met Department, worked there from 1985 to 2008. And then he worked for 4 years at National Atmospheric Research Laboratory under Department of Space. Then he moved to the newly established Ministry of Earth Sciences as a scientist advisor. And in 2015, he was for a short time director of the Indian Institute of Tropical Meteorology in Pune. Then he became the secretary of Ministry of Earth Sciences in 2015 and served there for 6 years. Professor Rajivan has made many contributions of interest to monsoons. You know, there's a strong tradition of statistical forecasting of the monsoon started by Sir Gilbert Walker more than 100 years ago. And around 2000 and 2002, the department found that the forecast was not working well. Things were falling apart. They couldn't predict the big drought of 2002. So Dr. Rajivan was involved in developing new statistical techniques which improved the forecasting a lot. In addition, he also was involved, along with statistical, to also look at dynamical models, which have become more robust now. So during this tenure in the ministry, he has championed both statistical and dynamical forecast model, and both are used together in the forecasting of monsoon, both short-term and long-term. He was also involved in developing the theory and forecast of monsoon onset, a very important event in the Indian monsoon. And during his tenure in the ministry, the forecast capabilities, both weather and climate, has improved tremendously. And today we can trust the forecast given to India Met Department over weather for the next few days. And even seasonal forecast, which is much more difficult topic, has also improved in this time. And Dr. Rajivan not only was involved in these two, he was also very much involved in making available to the public the rainfall data of India, which is very much valued by everyone around the world. So he's very famous for his 1 degree data that he generated, which is used widely by everyone in order to validate their models. Okay, and a person of this caliber is also, I'm happy to inform you, he is now writing a book on monsoons, which will be a authoritative work, because the last book on monsoon was published in 1976 by Y.P. Rao. He not had a book for almost 50 years. So Dr. Rajivan's extensive experience will be able to come up with a book which will give you the full insight into monsoon, understanding monsoon and forecasting monsoon. Today you're going to get a little glimpse of his great knowledge. So today he is going to deliver the 19th Jeremy Grantham lecture on the impact of climate change on monsoon variability and prediction. So I invite Dr. Rajivan to run through the lecture. Thank you.
Thank you, Professor Srinivasan, for first of all for inviting me. It's echo. Yeah, for inviting me as well as for a nice introduction to the audience. So I'll be talking today on mainly on monsoon decadal variability and prediction, and what could be the impact from climate change on these two aspects. You can interrupt me and ask questions if you want, and don't wait for ending the. And this is the monsoon rainfall data, which all of you know, most of you know, is the data from 1870. It's IAPM rainfall time series, which shows large variability. It's a year-to-year variability. All red bars are basically drought years, and all green bars are all excess years. We call flood years, and remaining all normal years. And over that, I plotted a line, black line. You can see that that's nothing but a 30-year running mean, and which very clearly shows there are epochs in which monsoon was below normal, and another epoch that monsoon was above normal, and another epoch it was again below normal. I don't know whether you have this one laser. Yeah. Let's see. So there is an epoch here where monsoon was below normal. Monsoon is below normal in the sense that the probability of getting a drought will be more here. There's more number of droughts in this epoch. And here, of course, we had 2 droughts, but the total number is small. And here again, we had a bunch of droughts. And you can see that this line was going up. So I remember in IMD there was a discussion, and DG at that time, Kurseshta, he was saying it's a good news, monsoon is going into a positive phase when Parthasarathi presented. But again, I did not really go into the positive phase. This years, because it's a central year, so all this drought has really pushed it down. So then we know that there is a large multi-decadal variability of monsoon, and this is from observations. And even if you so this is the first paper with Parthasarathi. I think I remember probably this was the first paper who Parthasarathi he did this, and he told that there are decadal variability. You can see that this epoch was poor, this epoch is good, this epoch is good. And also he plotted a graph which shows that kind of mean rainfall and standard deviation. When mean rainfall is more, standard deviation is less. And when rainfall goes into the negative side, standard deviation is. So less rainfall, but more variability. So that was a good point which he introduced. And if you really take data beyond the instrumental observations, for example, you take tree with the index chronology from 1481, and Thailand, same thing from Thailand from 1558, and our oxygen isotopic composition of speleothem from Central India, 625 to 2007. All this shows also a kind of a large multi-decadal variability. And the recent paper by Divakar Naidu, he also basically did this kind of analysis using proxy isotope of oxygen. And this is the first one, and second one is another proxy. So all these proxies of monsoon rainfall, which clearly shows that this multi-decadal variability is an intrinsic variability of Indian monsoon. And so if you really do a spectral analysis of observation, so you remember that Parthasarathi time series starts from 1875. But there was one scientist in Sondake, she was in ATM. She had developed data from 1810 also. So here, this is a blue line, and the red line is so-called Parthasarathi time series. If you do the spectral analysis in this paper by Rajesh Goswami, you can see that you get a lot of peaks in between 2 and 3 years, which is well known. Kind of a quasi-biennial oscillation of monsoon rainfall is well known. And but also you get a peak somewhere around 60 to 70 years peak. And both the time series, this peak is very clearly seen. So, and another small bunch of 5 to 7 years, that's all basically related to ENSO. ENSO comes in once in 5 years or 7 years. So you get a peak of 5 to 7 years. And recently there was a paper by Rajesh Goswami. He has done this analysis in a different way. So using that monsoon rainfall, he used a technique called empirical mode decomposition. And one time series can be decomposed into different modes of different time scales. And this method initially was proposed by a scientist called Huang, Huang, for seismology. And Professor R.N. Iyengar has applied it for developing models for Indian monsoon rainfall maybe about 15-20 years back. And IMD was using this model for long years. And this algorithm, slightly improved algorithm, but the physics is the concept is same. So what we can, this is the original time series, we can decompose it into different intrinsic, it's called IMF, intrinsic mode functions. IMF 1, 2, 3, 4, 5. 2 is basically a 7-year, 1 is basically 2 to 7 year cycle, and IMF 5 is basically a 65-year cycle, so it's a multi-decadal kind of oscillation. And that IMF 5, he tried to develop a kind of a regression with JJS SST, the global SST, and 4 regions were identified. One is here, this is basically a little North Pacific here. It's basically associated with the PDO, Pacific Decadal Oscillation. And second is basically over the Atlantic, and that is basically associated with the Atlantic multi-decadal oscillation. And third is from the ENSO region. It's a decadal ENSO variability, and fourth is from Indian Ocean. So these are the 4 regions they could get, and they say that this interdecadal, multi-decadal variability of Indian monsoon are associated with these 4 modes. It is triggered by Pacific oscillation, ENSO decadal variability, and AMO, and also Indian Ocean. And so I probably for your information, you know very well what is Atlantic multi-decadal variability. It's about 60-70 cycle. It is if you take sea surface temperature on North Atlantic and do a spectral analysis, you will get this kind of peak. And there are 3 patterns. It's a full AME pattern looks like this. Only tropical AME pattern looks like this, and only extratropical. So the maximum signal comes from extratropics. And this is the time series it looks like. And Pacific decadal is around 15 to 20 years time scale, and full pattern, Pacific decadal oscillation looks, it's almost like kind of an ENSO kind of signal. Only thing it's a little broader. You can see ENSO, the positive anomalies will be very close to equator, but here it is a little going outside to extratropics, and you have a cold anomaly here. This is the positive phase of video, and if it is in the negative phase, here it will be cold and here it will be warm. And so this is the first paper I remember who did this analysis on spectral analysis of Atlantic Ocean. And he did it basically with the temperature. And the 65 to 70 year cycle he was for. This paper is very famous. It's published in Nature, more than 1,800 citation now. This is the first paper which shows that there's a large scale multi-decadal variability not only for monsoon, the whole global system in the whole using astropher, he used the temperature. And this is a paper which used the same kind of analysis and must use the low pass retard JJS precipitation, 500 millibar vertical velocity, and 50 millibar winds, and under tropospheric temperatures. And basically, he correlated, regressed with the AMO, Atlantic multi-decadal oscillation index. And you can see that large signals are over Africa, North Africa, African monsoon. And also there is a large signals over Indian monsoon region, also in East Asian monsoon. So all monsoon regions are affected by AMO. So there's a good relationship between AMO and African monsoon, Indian monsoon, as well as East China monsoon. And also it is reflected in other variables like temperature as well as. So what it really does is it basically warms up the whole. When AMO is in positive phase, you have a warm anomaly here, which can control the remaining dynamics of the Indian monsoon. And of course, Atlantic Ocean, we know very well how Indian monsoon and Atlantic is related. This is a very famous paper. When I was just 1 year old, it was published by C. Ramasamy. He was there. but it is still it is a very famous paper, and so it's this is the circulation feature associated with the monsoon break. You know, we have monsoon active and break phases. When a break phase happens, there's a large scale trough extending from Europe to this, and that can pull up the monsoon trough towards foothills of Himalayas, and you can have a break monsoon. And this phenomenon is well known among IMD scientists, and many people have written papers. But we are not knowing that this is exactly coming from. We know that this is associated with the large scale western disturbance we call, and that also we know it's all origins from somewhere in the Mediterranean Sea and coming to east. So this relationship, basically, it all comes from Atlantic Ocean. So it's triggered by Atlantic Ocean. Atlantic Ocean plays an important role in developing this kind of troughs and ridges, and they can change the monsoon performance here. And of course, we have done a lot of work on identifying. You can see that there's a strong correlation over here, and also another paper which Srivastava also has done. So these indices are being used by IMD now in long range forecast. So we know on year-to-year variation, there's a good relation between Atlantic SSTs and Indian monsoon. So what now I am talking is basically on a multi-decadal timescale, a larger timescale. And so this is a paper from this institute, this is Bora et al. See, we know that there are ENSO with droughts, but there are droughts without ENSO. For example, 74, 79, there are years with this is one paper which are associated with kind of a Rossby wave pattern from middle latitude, and again the origin is again from the Atlantic Ocean. So on year-to-year variability and also intraseasonal variability, Atlantic Ocean plays an important role. And this is a very interesting diagram. So I remember I plotted about 15-20 years back, and I discussed with IITM. I remember. So this is the monsoon rainfall. It's just a 31-year running mean. It goes. This is a blue line is monsoon rainfall, and this yellow line is AMO. It goes very well. It is hand to hand. It goes. Only the last few years it did not go. When AMO went into the positive phase, still we had poor monsoon. Till then, it was going very well. So I remember I asked this question in this IIT meeting. Nobody answered. But then recently there was a paper by Sandeep et al. It's again IITM people. So they try to address this issue why the recent phase there is a kind of not going. Indian monsoon variability is not going. Sorry, Indian monsoon performance is not going well with the AMO. And so they took 3 epochs of 20 positive epoch. You had a good monsoon, and negative epoch, and positive epoch again. And they plotted the SST anomalies. You can see that in the positive epoch, of course, you can see that North Atlantic was warm. It's a positive phase of AMO, and this is negative phase of AMO. And again, this is the positive phase of AMO. So what they found more is this Indian Ocean warming. It was not seen here. So now, recent years, the Indian Ocean warming is here. So they put a hypothesis, as usual, many people do, is Indian Ocean warming means the temperature gradient between Indian Ocean and Indian mainland can reduce, because for monsoon to be good, so people assume that the meridianal temperature gradient should be good, which is not really true. It's not really true. Probably the origin of the monsoon, when monsoon starts, this temperature gradient is required. But once monsoon is set up, no more the temperature gradient plays a role. But many people die because it is an easy way to describe anything, to explain. Very quick way of explaining is why monsoon is not good because temperature gradient is weak. So this is the same paper. I'm not blaming him, but that's a style of writing papers nowadays. So they find a culprit here. They say the Indian Ocean is warm, so you have reduce the temperature gradient. And also they attribute to more parameter called North Atlantic subtropical high. That also has weekend, so that also is possible. So these are all hypotheses. So regarding hypothesis, I will tell a small story. I used to meet Professor Pishareddy. You all maybe, I don't know how many of you know Pishareddy. When I started writing paper in Ahmedabad, when I was in Ahmedabad office, I used to go and meet him PRL every week, every Tuesday. So when I showed some results, I said, so what could be the explanation? You say you make a hypothesis. You should be brave enough to give a hypothesis. And it is somebody else will prove that you are wrong. Okay. But till somebody proves that you are wrong, your hypothesis will remain correct. So you should be brave enough to give hypothesis. So I normally give hypothesis. Somebody else will prove that I am wrong. Okay. And this is the question is how the AMO plays a role. How AMO really influences in monsoon performance. So this is the AMO positive phase. You can see there are good monsoon rainfall, and these are negative phase of AMO. You have less rainfall. So what this paper clearly says that it can really affect the intra-seasonal variability of monsoon. So in the positive phase, there's a clustering of more of active spells, and in the negative phase of AMO, there will be a clustering of more of break spells. The blue line is basically the rainfall anomalies. You can see there are positive anomalies, and this is nothing but North Atlantic vorticity. You can go to just opposite of this. Just opposite to the rainfall anomalies. And this is just a reverse. This is just a mirror image of this break spell. So what this paper says that in the positive phase of AMO, there is a clustering of active spells, while in the negative phase, tendency of clustering of break spell is noted. And this also is very clearly seen here. You can see that this is also some around 35, the 35 events of positive AMO phase. You can see it's a kind of a lag analysis, lead lag analysis. You can see how the monsoon rainfall is. It's a positive phase, you get more rain. Active phase, you get more rain. And this blue line is the vorticity, apatopospheric vorticity over Atlantic, and this is over the Indian Ocean, Indian region. So you can see that a negative vorticity means it's basically an anticyclone, a kind of divergence, which is good for Indian monsoon. But this also goes well hand in with monsoon rainfall, but it's a kind of a leak of kind of a lag about of 1 week. And it is just opposite. The break phase, it will be just opposite of this. So they assume that the vorticity generation from North Atlantic plays an important role in terms of triggering Rossby wave along the middle latitudes and causing active and break spells. So that is the hypothesis which they give. And regarding Pacific decadal oscillation, there's good relationship now, and people have done, for example, the first paper I remember it was Krishna and Sugi in 2003. So you can see the difference between this is wet minus cold BMC composite of a PDO. You can see that it's a typical El Nino kind of distribution. Only thing it is a little more displaced to the extra topics, anomalies, and you have a positive anomaly here and a negative anomaly here. And you can see the ENSO composite, you can see this difference, spatial pattern is almost same, but the width is more. And when you do this rainfall analysis, this is subdivision rainfall analysis, you can see that the wet minus cold decadal composition, you can see how the rainfall is. When the positive phase of PDO, you get less rainfall, and negative phase of PDO, you get more rainfall. This is the first paper I remember that came out from this thing. And Krishnamurthy, I think she's his daughter. So these people have done plenty of analysis on the decadal variability, monsoon decadal variability. Like the Rajesh and Goswami paper, these people have also done the regression of JJ's rainfall into different components of this. And this is the AMO. First is AMO, and they use the multi-channel single spectral analysis, very powerful analysis method. And they get a trend, and they get a PDO signal, and also they get a new information from Atlantic. That is nothing but a tripole kind of thing, a negative anomaly, then positive anomaly, then followed by a negative. So this tripole is now becoming a very hot topic now. Atlantic tripole is not only on multi-decadal variability and also on internal variability. This tripole plays an important role. So plenty of papers are coming out now, and this is the area where people are now focusing. And so this is that. So they say that these are the phases, AMO, PDO, and tripole. They basically decides the multi-decadal variability of Indian monsoon. And so this is also same. It shows the same story. And this is the same story. But what you can see that this is the positive PDO. This is the SST pattern will be something like this, and you get more of rainfall. And sorry, less rainfall here, but in the negative phase of PDO, you get more rainfall. The El Nino, as you know that El Nino get less rainfall, La Nina you get more rainfall. So, and next slide, we'll show an interesting paper by interesting result from Krishnamurthy and Krishnamurthy. What they say that warm PDO and El Nino, what will be the relationship, and warm PDO and La Nina, what is the relationship? Cold PDO and La Nina, what's the relationship? Cold PDO and El Nino, what's the relationship? So what they say, during the warm PDO period, the impact of El Nino on the monsoon rain will be enhanced. La Nina, it will be reduced. So last year, remember that when we had El Nino, and also it was a negative phase of the PDO. So monsoon rainfall was poor, but it's not poor, not very poor as we thought of a ENSO signal. And so one hypothesis is that negative phase of PDO must have really helped monsoon to do a good performance, better performance than only El Nino was there. And so a positive positive warm PDO plus El Nino is really bad. You can see that it's both will reinforce the negative rainfall anomalies here, and the suppressed rainfall will be much more. And cold PDO El Nino will be, cold PDO and La Nina will be too good for Indian monsoon. And now question is, in the future scenario, whether how these relationships will work, how the monsoon variability will work. Frankly speaking, there are not many papers. I found out from Google Scholar only this paper. There's people, of course, this people, it's on Indian monsoon, but then they are not only focused on decadal variability. They focus on all time scales from day to decade. So they use the CMIP models and try to understand how in the future climate, what will be the what could be the variability in all these time scales. So this this you can see South Asian monsoon, JJ's precipitation variability. In all time scales, the variability is going to increase, especially in the decadal variability. So in future, what we, of course, monsoon internal variability we know. In future climate, we know that not only the mean rainfall will increase, and also we know the variability also is going to increase in the future. And but that is more relevant for even decadal variability. So when the future climate, as per this paper, it very clearly shows that decadal variability can be also more. That means the spread will be much more. And so this is the two papers I will mention about how this relationship between the decadal variability of Indian monsoon and relationship with the AMO and PDO can really influence the future projections of Indian monsoon. And and this one paper is again by Rajesh et al. They clearly say that if in the CMIP model, if the relationship of AMO and Indian monsoon is not good, it is going to affect the future projection of monsoon. So until you have a very good relationship between AMO and Indian monsoon and on present climate, on the present climate analysis, if the relationship is good in the model, the future projection will be far better. Uncertainty will be much less. So they say that unless this model improve to get this relationship good, there will be always an uncertainty. So this is the one example. They say this is the AMO and how this only observation blue line and how the models are performing. And this is for Indian monsoon. You can see that many models, this is observation, and many models do a far better, far more kind of a signal in the 60 to 65 year cycle. And this relationship between periodicity of monsoon rainfall in the model and also periodicity of AMO in the model. This is for CMIP 5. For CMIP 6, it is far better. It's about correlation is 0.61. The periodicity in the model is more in ISMR, and here also it's more. So this relationship, so what they find is that the biases in simulating the period of ISMR, multi-decadal variability are intrinsic to the models and are expected to persist in the future climate. And so the emerging constraint renders a 32% reduction in the multi-sample mean of projected increase, making the corrected future ISMR change is about 3.64. We know that 1% Kelvin will increase 7% of humidity, but as the rainfall is not exactly 7, it should be around 3 or 3.5 because the precipitation efficiency is much less. Whatever the more humidity may not really release into rainfall. It is about 3 or 3.5. But if you really analyze this IPCC model, the IPCC model project very high, large number. So they say if you really do this constraint of this relationship, it can be reduced to 3.64, which is reasonable. And it's the same kind of analysis done by Huang et al., but this is for PDO. So they also say the same story. Removing the IPO-related rainfall variation reduced the uncertainties in the near-time projection of South Asian monsoon rainfall by 13 to 15 and 26 to 30 in the two different models they considered. So our results demonstrate the uncertainty in near-time projections of the monsoon rainfall can be reduced by improving prediction of near future IPO and other internal modes of climate variability. So the model should really pick up these modes, multi-decadal modes of AMO as well as Pacific very well to see so that our future projections certainty will be also more. That's the message which goes. So I'll now the next phase I will talk about the decadal predictions. This figure, this cartoon is I think well known as this is a predictability sources and timescales. X-axis shows day, week, month, season, year, decadal, century, and this is a predictability source. And you can see the lower time scale is basically soil moisture, sea ice. In the subseasonal time scale is basically MJO and North Atlantic oscillation plays important. And this is our source of course, this is for the global weather, it's not for monsoon. And for a longer time scale between subseasonal and seasonal, stratosphere plays an important role, which we don't give much importance now. But now recent papers are showing that stratosphere also is becoming very, very important. And seasonal loss, we know that ENSO and CIs are very, very important. And intra-annual to decadal variability, Pacific decadal variability, AMB, and temperature, etc. And for a longer time scale on climate, deep ocean, greenhouse emissions, and land use. So S2S is well known. We know very well from subseasonal to seasonal timescale predictions, which we started about 10, 15 years back. Now it is very successful kind of experiments we are doing it. And we are able to operationalize S2S forecast now in India and anywhere else also in the world. So S2S forecast, we have done plenty of research and also we have developed the prediction systems which are doing very well. And there is a new area of research now coming is S2L. It's basically seasonal to interannual. And what I am talking is basically S2D, seasonal to decadal variability. This is the probably again first interesting paper done by Lord Mail. He has done a lot of work on decadal variability. So how can it be really skillful? And he said that it can be skillful. That was the message he has given in the paper was published around 2009, about 15 years back. And now a new concept is now available now in the research area. So near-term climate prediction, and a lot of efforts are being made now. Near-term climate prediction seems to basically operate between annual to decadal time scales, offer benefits on climate adaptation and resilience. And this I presented in DropMat, and I told that when we make climate projection, we make it for 2070, 2100, and say that monsoon is going to be good, but variability is going to be large, and also it's extreme rainfall. So question is, so what? So government may ask you a question, so what? So what I will do with this information? Prime Minister Office can ask you a question. Okay, good. 2100, we'll see. I cannot take an action now. Unless, of course, otherwise the basic mitigation efforts is a different issue. Reducing carbon dioxide, that's okay. But otherwise, for monsoon, as a monsoon is concerned, what action I can take? So policy people, policy makers like government, etc., will be more keen to know what next 10 years, what next 5 years monsoon will be. It seems that from IMD DG Mohabatra, I got to know that now ministries are asking for some energy sector people, Ministry of non-conventional energy sources. They are asking, what will be the energy availability after 5 years? End of this 2030. That's the question they are asking. So the people are more worried about next 5 years, next 10 years, because that is more practicable. So you can really do something very systematically, try to mitigate. 2100 is fine. So that I'm not saying that it's not useful, but much more useful is that next prediction for next 5 years, 10 years. So it's not only in Indian monsoon, many regions they now identify this prediction, this time scale is more important. Okay, so the evolution of the climate over the years and decades up to a century or so arises from three different systems, three different interactions. One is climate forcing, climate system external forcing from anthropogenic and natural influences. and interaction within basically in the internal variability, atmosphere, ocean, like AMO and all these things, and interaction between externally forced and internally generated variable, for example, volcanic eruptions, variation, solar flux. And this we do it for next many decades and century. We do the projections of future climate in the change of response of anthropogenic and natural forcing scenario, and we are doing it. Now the emphasis is on this near-time climate prediction, and where we make a skillful and reliable forecast of actual evolution of both externally forced and internally generated components of the climate system. That is the crux of this problem now. The question is, can we do? The answer is yes. And before that, I will tell what are the near-term climate predictability, what are the sources. And these are all sources. These are all red colors. Here, sources arising wholly or largely from initial conditions are shown as red, whereas sources wholly or largely arising in boundary conditions are pale green. These are all boundary conditions, but initial conditions are from ocean heat, meridian lower turning, ENSO, tropical oceans dynamics, and coastal oscillations. These are all from the initial conditions, from the internal system. And the external forcing is all the solar variability, also atmospheric chemistry, volcanic eruption. So these kind of things can really play a role on near-time climate variability. And this is the initial condition. So basically near-time climate predictability is a sum of, it has influence from both initial conditions as well as from external forces. That is the difference. And that is very clearly seen. So another paper which has come, and they have done a work with the community air system model and try to have a kind of a decadal prediction. They try to do it with their system. They made a 40 member ensembles for under 22 months. So it was a huge amount of computing, up to 3,000 years of model simulation they could do. And these are all just initial results. You can see that for the Europe temperature, you can see that JS rainfall, you can see that more or less the prediction is too good. And also this is for Sahel. So these are all very encouraging results. I will not say it's all excellent results, but the encouraging results. They skipped one button diagram. That's what I feel now. No. Okay, so here. So if you really want to do STDD, you have an influence from initial value as well as you have influence of boundary layer value. So you need to run the model with initial conditions, but in the climate change projection, we don't do initial conditions. We just run the model with any arbitrary input, arbitrary initial condition. But if you really want to be successful for STDD, you need to have an initial value problem, and you need to really initialize the models, and also use the boundary layer forcing changes in the boundary layer for next few years. So this is the difference between a kind of a decadal prediction what we are now talking. And there are experiments are already done, and this is one paper I showed, and this is another. Now there is a project under CMIP IPCC. They have a project called Decadal Climate Prediction Project. So when they made CMIP 6 projections, they also did a lot of prediction and decadal time scale, and these data are all available from this site, this CPP site. So they're talking about near-term decadal prediction variability. So a lot of experiments have been done, and a lot of hindcasts are made. And if you really want to do a kind of analysis to see that how skillful this decadal prediction, you can download it and use it. Data are free of cost. And this is a paper, very interesting paper, published in 19. They try to understand what is the impact. So if we know that for near-term climate prediction, you know initialization, and also you need a boundary forcing. So question is how important initialization. So this paper has done some simulation of temperature, scale, precipitation, and pressure for is a total skill. And what is the impact of contribution from initialization? You can see that temperature of the skill is too good. So decadal and the near-time climate prediction variability time scale temperature prediction is pretty good. You can predict very well. But precipitation you don't have that kind of scale everywhere. You can see the skill is good over Africa, and also of course it is in Europe and some parts of South American monsoon, but not in Indian monsoon. Only some few small spots you can get. But and see the changes in the initialization variability. You can see that Over Africa, you can see the monsoon region. The contribution of insulation is much more when compared to other regions. You can see that. So African region, if you really want to do a decadal prediction, you need to have an initialization model with initialization. Then only it will improve. This is for the same kind of pressure. And this is a meal again. Recently, he has published a paper. Here, he tried to do a kind of initialized system prediction. It's kind of seamless prediction from seasons S2S, S2L, S2D. And he used different models under the different resolution, 25 to 200 kilometer and 50 to 200 kilometer, and different models they use. And also they use different kind of ensembles. You can see that. And how many days of integration, 31 to 62 days, 6 to 12 months, and 5 to 10 years. And there he did a lot of research, and a lot of good results are coming, has come out. And I will tell you a few examples. One is the predictability skill from initial versus state versus external forcing. So this is if you really do without an external forcing, do it only with initial condition. And we all know that with the time, with the progress time, it will reduce a lot. So the skill will be too good or less than 2 years. Beyond 2 years, only from initialization you can expect any skill. So if you really want a forecast skill more than 2 years, you need to have a kind of component from external force. This is the message which has come out from this paper. And also how many ensembles you need. This is for S2S, and which we know that we need about, this is anomaly correlation coefficient. It get plateau somewhere around 8 to 10. So you need about 10 ensembles for a good forecast for S2S. But for this, for decadal prediction, it's much more. It's almost 20, 25 ensembles you need. You need more ensembles to have a better skill for decadal prediction. And also, this is a very interesting diagram. This is the black line is basically observations, the analysis data. So when you start integrating the model, how the drift is happening. This is blue lines are for 1 year, 2 years. The red lines are all 10 years. So after 10 years, when you start integrating the models, you go on getting drifted. And this is the actual realization after 10 years. So it is easy to say that we should have climate prediction models when there are issues. You need a huge number of ensembles. Drift is a major issue which we need to sort out. And WMO has recognized this area. And they have now have a Center for Excellence for doing decadal prediction, and they identified UK Met Office for doing this. So they do it regularly every year, every month they do, and they established it's called WMO Lead Center for Annual to Decadal Climate Prediction. It's at the UK Met Office, and they do projections for next 5 years, forecast for next 5 years. And these data are available global annual to decadal climate update. They do it every year. So I'll show you some examples. This is for surface temperature. And this green line, the blue lines are all projections, predictions for next 5 years. And this is for Atlantic multi-decadal variability. Also shows. Of course, a large spread is there. And also the spatial pattern I can show. This is for near surface temperature, ensemble mean. This is the probability of above normal near surface temperature. You remember that recently Albulimo has come out a kind of statement for next 5 years, temperature will be this much and anomaly will be this much. It will be one of the worst, warmest anomalies for next 5 years. So that all the inference has really come out from this experiment, this forecast. And this is for this is for sea level prediction. This is for precipitation. The precipitation, if you see the near surface, also near mean forecast for 2023 to 27, you got blue. So we should expect that a lot of good monsoon for coming years now. So this is a kind of way of doing it. And this is the skill. Don't see the skill. Skill is very bad. But temperature is still good for rainfall. It's not low, but you can see that African monsoon, there's a really good skill. I'll take another 10 minutes if so. So this is the question is how AMO, ISMR in CMIP model. So this is one paper, Joshi and 18. So they say that these are different kinds of models, and you know the relationship is positive. You see only a few models are picking up that positive relationship. That was not very high. The correlations are not that high. So they found only 53% of models simulate the observed AMO ISMR relationship, and some models fail, some models do well. And the models who fail to predict this kind of relationship is basically doesn't really link the Atlantic Ocean to Indian monsoon through Pacific. So that relationship is too bad. And this I'll skip. So now Wang et al., Bin Wang et al., instead of addressing a decadal prediction for a particular monsoon, they have a concept called land monsoon rainfall. So take all the land region where monsoon is there and take the rainfall data as a kind of an average. So it will be representative of the land monsoon over the land. And this is one of the index which they developed, just to take an average of all these things. And they try to develop the kind of hindcast for decadal prediction. And what they try to do, this is the decadal HMR index or the monsoon index, and they try to correlate with SSTs here. So they get the signal from, as we have seen earlier, we see the signal from Atlantic, IMO. We have a signal from here, basically decadal, Pacific PDO, and it's also ENSO decadal, and one from Indian Ocean. So they try to make some indices, this kind of indices they try to develop, 2 indices they develop. And it's an empirical kind of method, and this is the model which they could do it. So this is the black line is basically the observed rainfall, and red is basically reconstructed index, and remaining all predicted. So the model was developed up to 1960. So this is the hindcast, and this is the future projection. Not bad at all. You get some kind of up and down, but this is 0.71. And MSS is 0.40, which is reasonably good. And this is the score, how the compared to persistent prediction, that means you use only persistence to predict, and how the skill is. This is the persistence forecast, and how this hybrid prediction. They try to do a empirical method and also the hindcast from a dynamical model. That's what they call hybrid prediction, and hybrid prediction is pretty good. But this is only over land. So, but we don't know which monsoon is going to be good, because they average all the land regions together. And this is the last paper I will be discussing, is the recent paper. It has come out only some few months, August 2023. This is again from UK people, a UK team, Reading University. This study explores the ability of climate model from CMIP6, recent from decadal predictability experiment. Summer monsoon precipitation variability by using hindcast from Decadal Climate Prediction Project. And this is the one result which I want to show, that this is year 1 forecast, this is 2 to 5 year forecast, and 6 to 9 year forecast. You can see that year 1 forecast not much skill over African monsoon. But 2 to 5 years, that's a good skill, and 5 to 6 to 9 years is good skill. And also there is some good skill is coming for 6 to 9 years, only some positive skill. You can all read orange or red. You can see that is over Indian monsoon. And if you really do an area weighted average, you can see that the South Asian monsoon is not pretty good, but not very too good like compared to African monsoon, but it's on the positive side. So some kind of hope this model, this experiment is giving, that it is possible that we can have a reliable decadal prediction system for Indian monsoon. That's the message of the model this paper gives. So this also gives the same result. So when I was secretary, I started this decadal prediction group in IIT. Devi was director, and I think Dhanasheelan is given responsibility. Happy to see that one first paper has come out from this group, published only some last week or so. So they jumped into extreme precipitation instead of addressing the mean rainfall. They try to address the extreme precipitation, which will be much more difficult to see in the models. But they try to do that, and so this is the MMA. You can see that for different lead. This is from lead 1 mean 1 year, 2 year, 3 year, 10-year lead, and see this is the IMD observation. You can see that this model is. And it's picking up that kind of spatial pattern of extreme rainfall. We know extreme rainfall happens here. Okay, so this is well predicted. I'm not saying prediction is all hindcast. So it kind of model is really able to simulate this kind of spatial pattern. And also you can see the skill here, pattern correlation of radial distribution of precipitation events of extreme rainfall. All blue are good. You can see that it's all pretty good over here for last 60 to 12,000. So some kind of hope is there. So only thing is we need to further work on. So what are the challenges in decadal prediction is, as I told you, initialization of methods are very difficult. Because in the climate change portion, you need to initialize land surface, you need to initialize ocean, you need to initialize atmosphere, and to some extent cryosphere. It's all different time scale. So initializing different climate system, different time scale is really a tricky issue. And atmosphere, if you predict for next 5 years, next 5 days is easy because we have to initialize only atmosphere, very easy. But in this system, you need to initialize different climate systems of different time scales. Is one. And model error and drift, I showed that model has a lot of drift to go on drifting. So that we need to correct. So people assume that higher resolution model may really reduce this kind of drift in the climate change, in the predictability. And effect of land process interactions across various ocean bases and the role of stratospheric process. I think we Indians also should do a lot of work on stratosphere. Recently, a paper has come from Europe group that stratospheric process is important for seasonal forecast. And so when you really explicitly do a interaction between troposphere and stratosphere, the skill improves a lot. But not for monsoon. I'm not talking about it. It's a general predictability of seasonal predictability. So predictability of seasonal to decadal time scale is also associated with the different modes of variability in the atmosphere and ocean. Now, WMO as well as our whole research community talking about Earth system model. It basically the modeling of the whole Earth system, not of climate, not an ocean model, not a climate model, but a Earth system model. IITM, we have a Earth system model. So prediction also now people talk about Earth system prediction, not of a kind of a ocean prediction, atmospheric prediction. We always talk about system prediction. So it's kind of seamless prediction system which we are thinking. Challenges are plenty, and but I will be happy if we can really encourage young Indians to join the decadal prediction variability experiments here in India, so that more people are getting involved. Ultimately, I may not survive, but at least for next 10 years, we can have a reliable decadal prediction system for India. With that hope, I will stop.
Before I open the floor for questions, I just want to mention something which I forgot. For all the work he has done in his career, of course, he's got many honors, fellowship by the academy. But the most recent one this year, we got the Sir Gilbert Walker Gold Medal of the India Geological Society this year. So thank you for that. Okay. Now next for questions. Yeah.
Very nice and illuminating, very informative talk. Thank you. I was just thinking that in the tropics we have a lot more energy, isn't it? And atmosphere motion are coupled.
Yeah.
And the mid-latitude area is also smaller, and then we know that ocean is driven by the atmosphere mostly. So, and then decadal variability signals are in the mid-latitudes or the extreme or even far close to the poles. So what would be your comment on the source of this predictability where the heat content or the energy memory is so low?
I'm not sure, but I'm very sure that the source of predictability comes from latitudes and isotopics, where you assume that energy is small. But the experiments very clearly show, so far the experiments very clearly show, there is a promising predictability for tropics. And but I'm not sure how this source of predictability influences this predictability over the tropical region. I'm not sure about the physical mechanism. Exactly what is really happening in terms of energy, I'm not sure. But I agree with you that most of the source of predictability comes from middle latitude and isotopic. AME is basically a middle latitude phenomenon.
Yeah.
Okay. Any other question?
Yes, sir.
Yeah.
Sir, Tamil Nadu Chief Minister commented on
You heard that?
the wrong prediction, inaccuracy of the data. I think he don't know about the challenges what you have been facing. I think it has to be given back to him, sir.
Yeah, aware of that, right?
But
Heavy rainfall in Tamil Nadu.
Yes.
The government said IMD made a wrong prediction.
Right.
You're aware of that? That's what I said.
I'm writing an article in Hindu on Sunday, so you please read that.
That's good. Anybody else? On the other people, anyone? Yeah, please. You give a mic for the other people.
Good evening. Good evening, sir. Actually, I'm Zavaraja. Actually, my field is astrophysics.
Astrophysics.
In solar astrophysics. Actually, my doubt in the Rossby waves statement when the air goes to the when the air comes pole to equator, the tropical air goes to pole. So that leads to the formation of Rossby wave. So how it's different from the difference between the jet streams and the Rossby waves?
I think Ravi will give you a lecture, 1 hour lecture tomorrow.
That is not decadal, that's different time scale. And we will more time to explain it clearly.
Yeah, Rossby wave happens when jet stream gets jet stream basically is a zonal flow. If it gets disturbed and become meridional, you get a kind of Rossby wave pattern. So both are related.
That Rossby wave can be breakthrough or
Can be.
it can be go to unstable state.
Rossby wave is an instability phenomenon.
Due to ocean current activity.
It's not. I'm talking about atmosphere Rossby wave. Ocean, I think Vinay Chandran is there. He will help you.
Thank you.
Yeah. Yes, David. Yeah.
Yeah, so if you are looking at decadal predictability, right now we are using the same initial conditions as we use for a seasonal prediction.
Yeah.
Now, what additional kind of initial conditions will be needing? Will we need more from the deeper oceans also?
Deeper ocean and also to some extent to cryosphere. Because there are a lot of signals will be coming from snow, glaciers, and that kind of thing. Sea ice, especially sea ice. Sea ice, there will be a lot of signals coming out.
So all that we need to.
Yeah, and also deep ocean. Land surface. Yeah.
The question is, what's the model there? First question. And second, when you talk about policy, like from government, what actions can they take as of now? If you give, let's say, some prediction for the next decade.
Yeah, government can take a lot of decisions. So they may not tell you what decision they are taking, but and especially on economy of country, they can take a kind of corrective policy. For example, if you are saying the next 5 years there could be at least 2-3 droughts. So the economy is going to be affected. So they will have a kind of mitigation efforts. They will try to have a different strategy. And for agriculture, they will have different strategy of sowing, and they will find out different crops to sow. Because the monsoon rainfall will be reduced, and the amount, not only amount, the duration also will be reduced. So short-term kind of crops they will go instead of a long-term crops. So many policy decisions can be done. Even now they do it. Non-seasonal forecast when we give, they do a kind of policy decision they take.
Sir, thank you for the talk. I was just curious, the kind of models you are running for decadal prediction. What are their spatial resolutions? Because obviously we are only running it for 10 years or so.
150 to 200 kilometers. 150 to 200. You cannot run with 50 kilometers for decadal.
Like my idea was that you can skip parameterizations altogether and
skip.
No, if it's very high resolution, there's no need for parameterization. Right?
Oh, that you can. That concept is basically for prediction for next day, 1 hour, 1 hour, 2 hour, 24 hour, 48 hour. But decadal prediction, you cannot have explicit convection and not in the model. So I think I love job. You need a parameterization in that models. You cannot have explicit. Then you need huge computing power, which is impossible.
Okay.
Thank you.
Yeah, if there are no other questions, let's thank Raju.
Thank you.
Thank you.
Thank you. Thank you. Thank you.